Number sets. A set is a collection of unique objects called elements. By unique, we mean that the element cannot repeat. So we cannot have summer twice, or we cannot have two spiders. We use curly brackets to specify elements in the set. Since the order of elements in the set does not matter, set 1, 2, 3 is exactly the same as the set 3, 1, 2. Now let's look at number sets. The smallest number set includes natural numbers. These are counting numbers such as 1, 2, 3, 4, and so on. We use n, capital N, as a symbol for natural numbers, and we put all the natural numbers inside the curly brackets. Whole numbers include all the natural numbers, but they also include number 0. Next are integers with the symbol Z. It comes from German word Zahlen, which means numbers. Integers include all the natural numbers, 0, so all whole numbers, but they also include all the negative counterparts. So integers can be both positive, greater than 0, and negative, lesser than 0. It is really important to remember that all integers can be written as fractions with the denominator of 1, and this will be very important when we go into fractions. So we can write negative 3 as negative 3 over 1. We could also write negative in front and 3 over 1, or even the negative sign can be in the denominator. Take a minute and write integers as fractions in practice 1. Since natural numbers belong to whole numbers, there are subsets of whole numbers, and whole numbers belong to integers, so both natural numbers and whole numbers are subsets of integers. Next set of numbers are rational numbers with the symbol Q, standing for quoziente, in Italian meaning quotient. Remember, quotient is the result of division. Rational numbers include all the integers, whole numbers, and natural numbers. So natural numbers, whole numbers, and integers are subsets because all the elements inside them also belong to the rational numbers. So how do we know if the number is a rational number? If we can write it as a fraction, so a over b, where both a and b are integers. And of course b cannot be 0 because we cannot divide any number by 0. If that's the case, then this number is a rational number. The fraction is a rational number. Here we have a few examples. Negative 7 over 1. So negative 7 can be written as a fraction. Both numbers are integers and the denominator is not equal to 0. Here we have 0.25 can be written as a fraction of 25 over 100 or 1 over 4. So it's a rational number. 0.333, we see that 3 keeps repeating. We can also write it as 0.3 with a little dash on the top. That means 3 is repeating. And we can write it as 1 over 3 as a fraction, so that's a rational number. 3.5 can be written as 3 and 1/2, so it's a rational number. And negative 5.25 can be written as a fraction, negative 5 and a quarter. It can also be written as negative 21 over 4, so it can be written as a fraction. It's a rational number. So we see that decimals are either finished, finite, or terminate, like 0.25 or 3.5 or negative 5.25, and or can be repeating, like 0.333 repeating 3. So here are some examples of rational numbers where the decimals end, so 0.04 or 99, negative 2.6. And in example 4, we have rational numbers that where decimal places are repeating decimal digits. So 0.25 and 25 keeps repeating. So we can rewrite it as 0.25, 25, 25, and so on. And here 0.008 repeats. In both cases, these represent rational numbers. Okay, let's review how to convert decimal numbers into fractions. So if we have one decimal place, we write it over 10. So this is 1 over 10. Again, we have only one decimal place, so that's 2 over 10. And of course, we know that we have to simplify all the fractions. So 2 divided by 2 and 10 divided by 2. We get 1 over 5. What about this one? We have 2 decimal places. In this case, this is over 100. So it's 2 over 100. And we can simplify it to 1 over 50. We divide both numerator and denominator by 2. In the example above, we have 3 decimal places. That means this is over 1000. And in this case, we have no decimal places. That's why this is over 1. And of course, 99 divided by 1 is 99. To convert fraction into decimal, we can simply divide numerator by denominator, because remember that a fraction is simply a division. This is 1 divided by 2. But we can also change the denominator, or try to change it, into 10, 100, or 1000. So to get the denominator of 10 here, we have to multiply 2 by 5. And remember that whatever we do to the denominator, we have to do the same to the numerator. 1 times 5 is 5. Now 5 over 10, it's 0.5. Because we have 5 and we divide it by 10, so we move the point from here one space to the left. 0.5. Take a minute and try B. Once again, if we multiply 2 by 5, we get 10. And we have to do the same to the numerator, times 5. That's 5 times 5, 25. Now, to divide by 10, we move the point one space to the left. So 25 divided by 10 is 2.5. In the last question, we have 1 over 3. We cannot multiply 3 by any whole number, any integer, to get 10, 100, or 1000, or even 10,000. In this case, we would divide 1 by 3, and we would get 0.3333 repeating. So either we can put a small dash over 3, or we can put 0.333 repeating. Then we get to irrational numbers. Irrational numbers are separated from all the other rational numbers, including natural, whole, and integers. So there are not subsets of each other. So how do irrational numbers differ from the rational numbers that include natural numbers, whole numbers, and integers? It all started with a square root of 2 because it couldn't be split into a whole number of smaller pieces. So Hippasus found a number that couldn't be written as a fraction of 2 integers. Remember that rational numbers can always be written as a fraction of two integers, but irrational numbers cannot. Also, rational numbers, the decimal digits always end or repeat, and in irrational numbers, the decimal places do not end and do not repeat. So here we have a square root of 2, the first irrational number. Another very famous irrational number is the pi, which is 3.14. That's what we remember, but there are other digits that never end and never repeat. Notice that irrational numbers can also be negative. And this one looks like, oh, there are repeating patterns, but when you look closer, they do not repeat. Pause the video and find the answer to figure out which one represents irrational numbers. And irrational numbers have an infinite number of decimals. And finally, we get to the real numbers, which include all the rational numbers, which include integers, whole numbers, and natural numbers, but also include the irrational numbers. So we can say that rational numbers and irrational numbers are both subsets of real numbers. Now pause the video and work on practice questions 5 to 10 before we take up the solutions. How many integers are there between 0 and 1? So what are the integers? We start from 0, so this includes only positive integers. So these are the integers going to infinity. If we include negative, they also go to negative infinity. So how many integers do we have in between 0 and 1? Oh, well, there is no integers in between 0 and 1. How many fractions or rational numbers are there between 10 and 11? So we can split it into half, and we have 10 and a half. I'm going to put half only, so 10 and a half. But then we can split this into half, and then we have 10 and a quarter, and here 10 and 3/4. And then we can keep splitting the numbers into smaller and smaller fractions. And since we can split the fractions into smaller and smaller forever, we will have infinitely many rational numbers or fractions in between 10 and 11. And what about between -100 and -99? Once again, we can split this into half, so -99 and a half, but then we can split it into quarters, and then eighths and sixteenths and 32ths, and so on. So once again, we have an infinite number of rational numbers or fractions. In practice 8, we have two new symbols. This means that it belongs, and of course, when we have this sign crossed, it means does not belong. So does a 0 belong to the natural numbers? We see that there is no 0 in natural numbers, so this is false. Here it says that 0 does not belong to natural numbers. And that's correct because 0 is not a natural number. 1 belongs to natural numbers and integers. And we know that if it's a natural number, it's also an integer because all natural numbers belong to integers. They're a subset of integers. So since 1 belongs to the natural numbers, 1 must also be an integer. 10 and 100 belong to the set of integers. And since integers include all the positive and negative whole numbers, that is correct. Circle all answers that apply. Number 6 is natural number. We see that 6 belongs to natural numbers, so that's correct. And since all natural numbers also belong to whole numbers, 6 must belong to whole number. And since all whole numbers are part of integers, 6 must also be an integer. And since rational numbers include all integers, whole numbers, and natural numbers, that means 6 is also a rational number. The number negative 2.1 is negative. That makes sense. Positive cannot be. It's an integer. Remember, integers are negative 2, negative 3, negative 1, 0, 1, 2, 3. This is not an integer. Rational number. Since negative 2.1 can be written as negative 2 and 1 over 10, it can be written as a fraction. This is a rational number. Now, please pause the video and write the following numbers under the correct headings in the figure below. So let's try with the first one, 12. 12 is a natural number, so we write it right here. That means it belongs to whole numbers, integers, and rational numbers as well. Check your answers when you are done. And check your answers. An interval is a set of all numbers between two values, and we use regular brackets called parentheses or square brackets for those intervals. We use parentheses to show that the endpoint of an interval is not included in the set. And if the endpoint is included in the set, then we use square brackets. Intervals can be open, closed, or half open, depending on the endpoints, if the endpoints are included or not included in the set. Represent all integers between 2 and 8, not including 2 and 8, with an open interval. To show that the endpoints are not included, using the number line, we leave an open circle like this. So that shows that 2 and 8 are not included in the set. To use an open interval, we use regular brackets. That means that neither 2 or 8 are included in the set. We can also say that x is greater than 2 and x is less than 8, but neither 2 or 8 are included. We should also say that x belongs to all integers. Remember, integers are negative whole numbers and positive whole numbers. In the next example, we need to define all real numbers between negative pi and positive pi, and we want to include pi but exclude negative pi. To show that negative pi is not included, we use parentheses or regular brackets, and to show that the pi is included, we use the square brackets. On the number line, we use unfilled circle to show that negative pi is not included, and we use a filled circle to show that positive pi is included. We also can use this notation: x is greater than negative pi, and x is less and or equal to positive pi. So remember, this means x is less than pi, but if it also includes pi, we have to add another line. So x is less and equal to pi. And in this example, x belongs to all real numbers. So x belongs to all real numbers. This representation is called interval notation. This is a set notation. And here we use a number line to show the set and its intervals. In practice 13, we need to represent the set notation where x is greater than or equal to -4 and x is less than 3. Remember, this means this side is less and this side is greater. If it's opposite, this is greater and this is less. Where x belongs to all real numbers using the interval notation. So we have to figure out what kind of brackets we are using. So -4 on one side and 3 on the other side. These are two endpoints. Now, since x is greater or equal to -4 belongs to the set, but 3 does not belong to the set because x is less than 3. So -4 is the part of the interval and 3 is excluded. Represent the interval using the set notation. All right, so we're using the greater, lesser signs. The x is greater than, but also, since these are square brackets, it's equal to -pi, and x is less than, but also equal to, because again we have square brackets, to +pi. We also need to state that x belongs to all the real numbers. In this case, both endpoints are included. We can also have infinite endpoints. That means that the value of an endpoint is infinity. If infinity is used, there is no limit or no bound in that direction. Here we have an interval starting at 0, including 0, and going to infinity. But notice it does not include infinity, but it goes towards infinity. So x is greater equal to 0 and x is less than infinity. And x belongs to all real numbers. Try the next few practice questions on your own, so pause the video, and when you're ready, check your solutions. How many whole numbers are between -pi and 2pi? So first we have to remember that whole numbers start from 0 and they're whole integers, positive integers. We also have to remember that pi equals to approximately 3.14. So if we start from -pi, we are starting from -3.14. Then we have -3, which is an integer but not a whole number, -2, -1, and now the whole numbers begin. The whole numbers begin with 0, 1, 2, 3. Next we would have a whole pi, which is 3.14, but we are looking until 2 pi, which is times 2, 6.28. So we continue with 4, 5, 6, and then we get 2 pi. So we have 1, 2, 3, 4, 5, 6, 7, 7 whole numbers in between negative pi and 2 pi. How many even numbers are between 5 and 61? Okay, I don't want to write all the even numbers between 5 and 61. So let's simplify it a bit. Let's say it's between 5 and 11, right? So I can write the numbers, even numbers between 5 and 11. These are 6, 8, and 10. So I have 3 numbers. So how can I get it without writing them down? So first we have to subtract 11 minus 5. This will give us the number of numbers between 5 and 11. So 11 minus 5. But since we're only looking for even numbers, it's half of all the numbers because we have even and odd. So we have to divide it by 2. So 11 minus 5 is 6. Divided by 2 is 3. Now we can follow this to find how many even numbers we have between 5 and 61. So 61 minus 5 divided by 2. So we have 28 even numbers between 5 and 61. How many even numbers do we have between 5 and 62? Remember, when it says between, the 5 and 62 endpoints are not included. So just between them. So again, let's look at between 5 and 12. Remember, this does not include 12. So we have 6, 8, 9, 10, then 11 and 12. So 12 is not included. So once again, we have 3 even numbers between 5 and 12. So how do we do that? If we do 12 minus 5 divided by 2, we get 7 over 2, which is 3.5. This cannot be our answer. So in this case, we have to subtract 1. And we get 6 over 2. This type of questions, 16 and 17, often show on different competitions. These are interesting questions. So here we do 62 minus 5 minus 1 divide by 2. And again, if you use small numbers, you can figure out the formulas. So again, we have 28 even numbers between 5 and 62.